Hello, everyone. I am back, Mr. Hine, and this one is on 312, which we're getting to the real big concepts of calculus. And today and the next video, which you'll see on Monday, are really going to get into, I'd say, one of the two biggest things that calculus is. All right. Now, what this lesson is on is talking about how we're going from a secant line to a tangent line, or what will be known moving forward as AROC to IROC, which is the average rate of change to the instantaneous rate of change. And I'll explain that in this video. But first things first, just a recap from the last video is we now know the power rule. And this helps us get the slope function for any polynomial. So for any polynomial f of x equals a times n, or a times n, a times x to the nth power, where a and n can basically be any real number, all right? The slope function can be found by doing f prime of x is equal to a times n x to the n minus 1. And that is a very cool observation thing we discovered, is that we can map the slopes of a polynomial with a new function, and that new function always follows this rule, is that if you multiply the exponent times the coefficient in front, and then it becomes that function of one less degree. So from quadratic down to linear, from a cubic down to quadratic. And that is very, very helpful and useful to us, all right? So that's the power rule. Now here's some examples of it at play, and you saw it in the last video, and this video goes into just more examples on it. So say the function is 3x to the fifth. Well, that means that its slope function will be represented by f prime of x is 15x to the fourth. And that is the slope function there, which is fascinating. So just as a reminder, that means like if I plugged 1 into this, if I plugged in 1, I would have, f prime of 1 equals 15. And what that's saying is that on your original function f, that the slope at 1 is 15. And that's what it's saying, which is really awesome things, all right? So these slope functions are very helpful to us. If you look at the next one, the slope function of 2x to the third minus 6x squared is, if we look at two different functions, it just gets applied to each function on its own. So this, we can look on its own, which would be 6x squared. And this over here will be minus 12x to the first, but you don't really need to put to the first power. We can just put minus 12x. What about for c? c here, the slope function will be 50x to the ninth minus 7. Now, I could put x to the 0, because remember, that's a 1. But remember, anything to the 0 power is just 1, so I don't need to put that. And what about the plus 1? All right, so plus 1 coefficients actually just have a slope function of 0, so there's nothing there. It's just 50x to the ninth minus 7, all right, because the rate of change of a constant is 0, so the slope function there is 0, all right? And then we go to the next one. Well, even if you didn't want to know, let me just explain this. So originally, this is like, you can see it as 1x to the 0 if there's no number there. Well, notice when we follow the power rule, 0 times 1 will make that 0x to the negative 1. But 0 times anything is nothing. So that's another way of seeing that it's 0 always at the end there. Right. If we go to D, this slope function, if there's a horizontal shift, that just means we still take the slope function, just keep the horizontal shift in place. So it'll be 2 times 3, which is 6. Horizontal shift stays the same, and then that goes to a power of 1. For E here, the slope function will be 4x minus 1 to the third plus 10x. And hopefully you're catching on to these. And this last one will be negative 3x minus 2 to the negative 2, right? Because like I said in the power rule, it's not just positive integers. Sorry, it's not just positive integers. It can be any real number, right? Where we actually wanted to rewrite this better, that's more commonly written as negative 3 over x minus 2 squared, because a negative power is just how many times we're dividing that. Okay? So that's the power rule and how that works, and us using that now. But now we get to the real meat of this chapter and a real big part of calculus, and that's going from secants to tangents. Right? Now remember, and I'll explain this in a second, that the slope of a secant line, so recall that the slope of a secant line is the same thing as its average rate of change. And if we just look at the first letter of average rate of change, that's how the acronym AROC comes to be, which we call AROC commonly in this curriculum. Right? And then the slope of a tangent line, and I'll give you a graphic to help you see this soon, is the rate, is the instantaneous rate of change, which if you follow those first letters, it makes the acronym IROC. All right. And hopefully when I said all this, a secant line, you know, that's where it hits the graph at 2 points, hits graph at 2 points, and a tangent line only hits graph at 1 point. It's the graph at one spot. So what we're doing is we're going to be going from the average rate of change to the instantaneous rate of change, from a secant line to a tangent line. And this is how we're going to build and use this knowledge to get something happening at the exact moment. If I want to know how fast you're traveling at, you know, t equals 1.5, I can use this definition, which we're going to learn about right now, to get it. Now here's a graphic to help you see it. We're going to go through this together. Say that I had an arbitrary curve that looked like this. Right? Arbitrary, random, I just drew it. Right? Some function f of x. Right? And say I wanted to find the rate of change, or the slope at x equals 1, 2, 3, 4, 5, at 5. Right? Say I wanted to find what's the slope or rate of change, right? It's a better word. What's the rate of change at t equals 5, where this will be time in our problem, and say this is velocity. Let's not do velocity. Let's do distance. So we want to know in miles. Let's try and make this as common for you as possible. So we want to know what's his mile per hour at the 5th hour. All right. What's the slope rate change at t equals 5? Now, we use this idea that we were doing with local linearization and secant lines to help us this, because if we zoomed in at this point, it will look very much like a line. So what we can do is we can pick a point right to its right side of it, some distance h away. So some distance h away, h being any number. So this will be the point 5 plus h. So I don't know, say, if you're 0.1 away, then this will be 5.1. If you're 0.02 away, then that's 5.02. And what we're going to do is we're going to find the slope of the secant line there. And I know it's hard to see, but if we pick say, if we looked at the slope, write this in words. If we looked at the slope between 5 and 5.01, well, we're going to be pretty darn close. We'll be pretty darn close to the actual slope at t equals 5, right? Because if we pick a point just a little bit away and we find the slope between those 2 points, if we find the slope of that secant line, we'll be pretty close. In fact, how do we get closer is, what if instead of looking at 5 and 5.01, what if we tried to do the slope? And when I say slope, notice that it's between 2 points, so it's the slope of a secant line. What if we found the slope of a secant line, between t equals 5 and t equals 5.0001? So we pick a point that's even closer to 5, where h is even smaller, that distance away we're even smaller. Well, what's going to happen is that slope, or let's start using the proper word. Instead of slope, remember that the slope of a secant line is the same thing as the average rate of change, the AROC. So if we now do it 5.001, a little bit closer, the average rate of change will be even closer to the instantaneously rate of change, right? Because when I say actual slope at t equals 5, that's the IROC, that's what's happening at that moment. And the slope between these 2 points, well, that's the average rate of change, the AROC, right? So we're getting even closer to knowing the value and the slope at a particular moment, the speed, the rate of change at a time. In fact, what if we even got closer? So if we did t equals 5 and say t equals 5.000001, now we're almost looking at a point so close to the naked eye, we can't even see a difference between those points. With a slope between those 2 points, the average rate of change there will be even closer to the instantaneously rate of change, all right? So how do we build all this knowledge that as we get closer, the average rate of change is getting closer to the instantaneous rate of change? What's happening to the h, like that distance away? Well, that distance away has to get minimized to 0. Well, how do we minimize something to 0? We use limits. And this right here is the definition that we're going to use. And I'll explain it a little bit more on the back with more space, is to find, scratch this, let's go on the back side, use more space, because I'm running out of space, and this is so awesome and so big that I want you to understand this. So draw my arbitrary curve again. And we want to know the IROC at t equals 5. We want to know what's the velocity at 5. All right. What we can do is we can use the secant line and a point very, very close to approximate. And the knowledge they use is they say like a point, 5 plus h, that's h away. Use secant lines. So then if we look at that point there and there, we find the slope between those 2 points, we'll get even closer. Right? But to get the most perfect example, what's going to happen to your h is it gets smaller and smaller and smaller. In fact, we want to approach 0. So what we write there is to get the instantaneous rate of change at a particular moment, we use limits. And we say the limit as h approaches 0. So as that distance between these 2 points that we're picking minimizes to basically nothing, that the slope between these 2 points will, and then we're looking at the slope between those 2 points, which is f of 5 plus h minus f of 5 over 5 plus h minus 5. Now, I think I just lost you there, and I'm not going to remake a video, so let me explain that. What's the slope? We're finding for the secant line, the average rate of change, the slope between these 2 points, well, this point is the point 5 plus h, comma, f of 5 plus h, whatever the function is at that x value. And this is the point 5, comma, f of 5. So what we're doing is if we're finding the slope of the secant line here, we're finding the slope between 5 comma f of 5 and 5 plus h comma f of 5 plus h. Right? And how do you find slope? It's the change in y values. So it's y2 minus y1, f of 5 plus h minus f of 5 over x2 minus x1. So what's happening is we're finding this. So this whole thing right here, well, that's just the slope of the secant line. You know, h away. And what we're doing is that slope of the secant line, we're minimizing that distance to 0, so then we get the instantaneous rate of change. Right? And that right there is how you go from secant lines, which we know how to do, to instantaneous rate of change, is combining secant lines and limits. All right? And that's really, really amazing stuff. And we explain this more definitely in the coming days, but that is one of the biggest definitions of this class. So, preview of next week. Let me show you how this works in a problem, as this might clear things up. So, say we wanted to find say there's a velocity function. Now, let's say there's a distance function represented by x squared. All right? And I want to find the velocity at t equals 2. All right, not the average velocity. I want to find the velocity at equals 2, which is the instantaneous velocity at 2. Right? Not the average rate of change from 0 to 2. All right? Now, remember that velocity is the slope of this graph. So basically what I'm saying, in other words, i.e., what's the slope at t equals 2? Okay. So how do we do this? Is we're going to pick 2 points, and those 2 points we're going to pick are 2 comma d of 2, and the other point being 2 plus h comma d of 2 plus h. Right? And we're going to find the slope of the secant line here, the slope between these 2 points, right? Between these 2 points, and use the limit as h approaches 0 to minimize that distance between these points. Right? So using what we just did up here, it's going to be the limit as h approaches 0 of d of 2 plus h minus d of 2, that's the y values separating each other, y2 minus y1, over x2 minus x1. Okay. Now we simplify this. So then we get the limit as h approaches 0 of, well, what's d of 2 plus h? So we just take 2 plus h and plug it into the function. So then that's going to be 2 plus h squared minus d of 2, which you plug 2 in, so that's just 2 squared, over. Now, one thing that you'll see is that when we do 2 plus h minus 2, notice that the 2 and the minus will always cancel out, so we actually always are just left with h on the bottom. And that is a further definition of it, but I don't want you to necessarily memorize that. I want you to see where it comes from. All right, let's keep going. Limit as h approaches 0. Now, 2 plus h squared, if we multiply this out, you'll have 4 plus 4h plus h squared minus 4 all over h. The 4 minus 4 will go away, so then we're at limit as h approaches 0 of 4h plus h squared over h, in which we can factor out an h and write that. And I'm going a little bit slow. I'm sure you might be able to go quicker once you start to see the pattern here. That would make 4h times 4 plus h over h, which those h's would cancel, which they should always cancel because we can't plug in 0 here because you can't divide by 0. So what this ends up becoming is the limit as h approaches 0, 4 plus h, in which now we can plug in 0, and you get 4. And there it is. That means that the velocity, or the IROC here, at t equals 2 is 4. And I know what this problem is, like miles per hour, for example. And if you look back at what we did yesterday, when we did the table XM, you'll see that when you explored it at 2, the M was 4. And we just did that through its actual definition now. Awesome stuff. It might feel like a lot, but understand what's happening here from a conceptual standpoint, because if you understand from a conceptual standpoint, there's not as much to memorize, nor do you really have to memorize it. It's to get the IROC, you find the slope of the secant line from using 2 points where 1 point is h away. That's where I get like the 5 plus h. And then just we want to minimize that distance between the points. That h, we want that point to get even close to that point. So we're looking at 2 points that are virtually the same point because they're so close together. All right. Awesome stuff. I hope that helps you. Definitely ask questions. Hope this video wasn't too long and it made some sense to you. All right.